Your absent-minded professors here, and the second half of the semester is ready to go. We did not release exam 1 before last time, but this is the breakdown. I thought that a lot of people did quite well on the exam. The only thing that sort of concerns me a little bit is sort of how wide the spread is. And so, but in general, we try and target like a mid-60s overall average, and we were close, and a number of people did quite well. And so all your grading requests are on Gradescope. Any comments on the exam at all? No comments? Okay, so here is, some of you may have heard this before, but we're not done with the exam. We're not done with the exam. We do something in this class called the deal. And so let me tell you a little bit about what the deal is. So here is, the deal. And the deal is that no exam 1 solutions, it wasn't because we were lazy, we do this on purpose. No exam 1 solutions are going to be posted for a while. You have the opportunity to choose up to 2 questions. There were 7 questions on the exam. You can choose 2 of them. You can redo your answers to those questions on the exam. And you can hand in your answers, and you can talk with the staff, talk with your friends. You just get the answers right. It would be unfortunate if you handed in an answer that wasn't correct this time. And it needs to be handed in by Friday, April 8th, which sounds like a lot of time. And if you do so, you'll get back 50% of the points that you missed. So obviously, people choose the problems where they lost the most points. So does this make sense? Yes?
Do we have to repeat the questions we got right in the question?
No. That's probably fine. I mean, but yeah, hopefully that's not that big of a deal. Yes, so you only need to redo the ones that you missed. So the point of this is normally you hand in an exam, and there's stuff you don't know, and you're like, oh, that's too bad, I didn't know it. Not eligible for a regrade request, and you just like throw it out, right? So you don't learn anything. So here you get to learn 2 of the questions. Seem like a good deal? Okay, good. But here's the catch. The catch is you must hand in your solution to the course staff at an office hours. Doesn't seem like that big of a deal. But you are not allowed to hand in your solution unless you're able to answer any question I ask you about the exam, or any question my TAs or the other professors and the staff ask you about the exam. So if I decide to ask you a question about something about question 1, or maybe something slightly related to question 1, and you cannot answer that question, I will not accept your hand-in. That's the deal. And you have, yes?
Is that like only once, or can you retry?
You can try this as many times as you want. However, they need to be handed in by Friday, April 8th. And we're going to create slots for this, like 7-minute slots or so to talk to you. And I can guarantee you that we're only going to create so many slots. And the oversubscription rate with 160 people in the class will not be a factor of 2. So I suspect, I advise you to say that if we create maybe 200 or 250 slots to give you the opportunity to do this, that's about all the slots that we're going to create. So you're welcome to do this at any time, but you probably will only have a limited set of opportunities to do so. So I recommend when you come in, you should probably know all the material on the exam. Any questions about this? Nope. Okay, so this has been something that students have enjoyed in the past because some people have come in, I've asked them a question, they've kind of gotten it right, but they didn't come back, they didn't get it perfectly right. I went ahead and gave them the credit, and then they came back anyway because they wanted to answer the question better. Well, there were 7 questions on the exam, so you can choose any of the 7 questions. So I guess big problems probably about the question. Yes?
Would the questions that we get asked be the questions that we want regraded?
No. They will certainly not be the questions that you get regraded. Because the whole point is, if you demonstrate to me, like in the same way that if you demonstrate that you did the practice solutions, I gave you the solution. If you demonstrate that you know the material on the exam, I'll give you some points back. Okay. Yes, and there'll be, like 6 or 7-minute interviews. Anyways, okay. So let's get started with today's lecture. So everything that we've talked about so far in class, we have assumed that there was this magical connection between all the processors. And in many of the lectures, we assumed that said magical connection was a bus. So our mental model was that, let's say we had a processor over here, and it had a cache. And we had another processor over here, and it had a cache. And there was a connection between the two, which we often said, let's just think about it for simplicity, as if that connection was a bus. Right? So, and the bus had some clients, such as the caches, such as the memory system. And the bus, I told you to think about as, well, a bus is just a big bundle of wires that which we can send messages over. And for example, maybe there might be a bundle of wires for commands and addresses. There might be a bundle of wires that carries the cache lines whenever when responses happen. So we had this big bundle of wires, and there was an arbitrator that only allowed one client to send its information on those wires at the same time. And often in class, for example, when we were talking about cache coherence, we kind of said that, look, only one client, one student in the classroom can shout out at one time. That was our mental model of what was going on. So today we're going to change that a little bit. And we're going to say, a bus is only one possible way to connect all these processors. And we're going to move that today to a more modern notion of, hey, it's just some interconnection network. And so I drew this as a cloud because the distributed, the internet people often draw the internet as a cloud. It's an arbitrary network connecting the various clients in the system. And we're going to talk about a couple of different topologies for that network today. So now I have a network, and I have different nodes on the network, different processor caches, memory, other things like maybe like the I/O bus or something like that. So our network on a chip, I want you to think of now as every modern multi-core processor, whether it be a CPU, GPU, anything, it's going to have a network on that chip connecting the various nodes. And those nodes might be processor cores with other cores, caches with other caches, I/O devices with the rest of the system, and so on and so on. And so why do you think the design of this interconnect might be really important, given what we've seen so far in class? And what are some of the things that have fundamentally limited performance in some of the applications that we've talked about? Obviously, workload imbalance has been one. What else has limited performance? Latency of accessing different components of the system. And so what's been one good example? So memory latency was one example. In the context of maybe cache coherence, what was an example there?
So if you get like a NUMA architecture, then accessing someone else's cache is a heck of a lot more expensive than
Right. I mean, with a NUMA example, I would say actually accessing a remote partition of memory. But it's absolutely true, is depending on where the data sits, we have a protocol. The cache coherence protocol was a prescription of how the caches need to communicate before anyone can proceed. And obviously, if the interconnect cannot efficiently handle that traffic, that communication traffic, or the fundamental traffic that's needed to load and store data from memory and so on, things are going to be slow. And so these days, the network can very well dictate how large of a system can be built, like how many cores are we going to put on a processor, how easy is it to add more cores to a processor, and can be very important in terms of the overall performance of the processor, and very importantly, how much energy it takes to carry out these communication operations. So, and if you look at some of these modern processors these days, the core count's getting quite high. So in all of our laptops, we probably have a dual core, or maybe a quad core chip. We have Xenon Phi you got some experience running on an old version of Phi last assignment. The new version of Phi is a 72-core chip on one processor. We'll talk about that interconnect. If we go to your mobile phones, so this is a pretty high-end mobile phone, but we see 4 cores, a tiny little core, and a whole bunch of these GPU execution units as well, and they're all interconnected. These Tylera chips are things that are seeing some use in cell phone base stations and stuff these days for media processing. So there's a lot of different nodes that are now popping up on these chips, and they all need to be interconnected. They need to be connected somehow. So let me start with just a little bit of terminology to make sure we're all speaking the same language here. Has anybody had networks actually here at CMU? So some of this may actually you've already seen in other classes. Anybody taking a networking class here at CMU? You taking a networking class? You taking that one? Yeah, so you probably have heard about a number of these things so far. So I'm going to say that a network node is a client that's attached to the network. So in the course of this lecture, you can think about the network nodes being processors, or the memory system would be a node. Or if you don't want to think about processors, you could probably think about the processor's cache being a node on the network. So I'm going to always draw the network nodes as these green circles. There is an interface between the network node and the network is composed of a number of links that are connected via switches. And so a switch just connects multiple input links to multiple output links. And depending on the configuration of that switch, a message on one link might get routed to other output links. Okay? And a link is perfectly reasonable to just think of a link as a bundle of wires connecting two nodes in the network. And so there's going to be some design issues that we'll talk about today, which is what is the form, what is the topology in which all of these nodes are connected? We're going to talk about some real basics on how, given this graph, if I want to send a message from point A to point B, how do I route a message from point A to point B? And as part of that routing, not just how we send the message to the network, but in fact when and how we control the flow of the bits and pieces of these packets as they go through the network. And so if I look at a network, for example, this network here, does anybody know what kind of network that is? No? What would you call that? Yeah, or mesh, and we'll get to the terminology in a second, is you might ask the question, which actually you did this in assignment 3, is I gave you a graph, and we asked you to estimate the diameter of the graph. And the diameter of the graph was the maximum distance between any two nodes, and that's an important metric of thinking about any network topology. So here in this mesh network, which is a 4x4 mesh, the diameter, the maximum distance between any two nodes is 6. And why am I claiming that it's 6? Do you agree? Everybody agrees? So you're nodding. Why are you saying it's? Sure, exactly. I could take like 3 hops to get across the horizontal and another 3 hops to go vertical. So the worst case scenario is to send from the top left to the bottom right, or vice versa, and that's 6 hops through the network. You also might be interested in like sort of the average distance between any two nodes in the network. Okay, and then there's another property of networks, which is not super critical, but unless you're really a network designer, but interesting, is whether or not a network is considered to be a direct network or an indirect network. So a direct network, every node, every switches and nodes are the nodes are inside the network. So here in this mesh topology, you'll notice that every node is a switch. Here in this omega network, you can think about the nodes being outside the network, and the switches are routing between those nodes. So the example on the left, we call a direct network. The example on the right is referred to as an indirect network. Okay, so there are a couple of properties. So diameter was one interesting property of a network. Was diameter a metric of bandwidth or latency? It's probably much more pertaining to latency because it's the maximum number of hops between a point A and point B. An interesting metric of bandwidth is the bisection bandwidth. And you can think about the bisection bandwidth of a network as if you made any cut through the network. What are the maximum number of wires that you cut? Or what's the maximum bandwidth between one side of the network to the other if you made any one cut? So if I go back to sort of this example, if there are n squared nodes in this network, and I made a vertical cut, what would you say the bisection bandwidth of this mesh is? Well, 8, sure. If this was 8 squared nodes in the network. Right, exactly. So it would be n. Because you'd be cutting, you'd only have O of n links connecting both sides of the network. So the maximum amount of information that you could get across that network was O of n. Any idea what's on the right? It's actually similar. It's n over 2, actually. In that case. I mean, it's O of n still, but it's n over 2. OK, so the other interesting property of a network is not just its bisection bandwidth, but whether or not it's considered a blocking or non-blocking network. So let me give you this example of this network. We're not going to talk about what it is yet. Imagine I had to send 2 pairs of messages. I want you to send messages from 0 to 1, so node 0 to node 1. And I'm drawing I'm duplicating the nodes in my diagrams. So this is like sort of how a node inserts information into the network. And you can think about this being how the node receives information from the network. So if this was actually laid out on a chip, there obviously wouldn't be 2 processor 7s. There would be a wire that comes back around to here or something like that. So tell me how, if you were to send a message from processor 0 to processor 1, how might it get routed on the network? Simple question. Yeah. Just goes right across the top. Very easy. And if I wanted to go from processor 3 to processor 7, how might that work out? I'd start 3. I would drop to this switch, and so on and so on. So can I send a message from 0 to 1 at the same time that I send a message from 3 to 7? Yes, right? Because they're using completely different resources. It makes sense for the network to be able to sustain those 2 communications. So, but what about if I want to send from 1 to 6, 1 to 6, as well as 3 to 7? So 1 to 6 and 3 to 7. Yeah.
They can't go backwards at
Well,
all?
so 1 goes to 6, 1 here. Then that would get routed to this node. And then it would get to this node and then go to 6. And then 3 to 7 is the other one I said, right? So 3 to this switch, to this switch, to this switch, to that switch.
Go 1 to there, and then back down there.
Say it again.
Sorry. I don't know how to explain it though. So like 1, then the
1.
Second, there, and then you would go down there.
Oh, I see.
Yeah.
All right, so you could come up with a different routing policy. That's true. So you could reroute one of the messages. In this network, no. I should have probably drawn edges in that direction. So the assumption was that the messages are only flowing to the right the way I drew this. Because if you wanted to get there, you would go and then remember that 4 wraps around to here. So that's a good point. I should have been more. And so in this case, there's contention, right? So this notion of a blocking network is a network where I can't connect up. The message that I want to send between A and B, it depends on other messages that are being sent in the system. So in this particular case, for example, the messages might travel concurrently to this node, and then one of them may need to get blocked while the other message went through, and then it came through. Then the second message would come through at a separate time. More advanced networks will have will dynamically reroute messages, maybe to ensure maximal performance. But in this particular case, the latency of 0 to 6 might be variable based on what the other messages are being sent in the system at the same time. And not all networks have this property. Another interesting property to think about networks is that, and you'll find this in assignment 4, and I showed a slide. Remember the slide right before in class last time? We were talking about Memcached, and we talked about how Facebook could sustain this throughput at acceptable latency, and a higher throughput, and it said at unacceptable latency. So we talked about how you can make design decisions to improve throughput, often at the cost of latency. And you'll see that behavior in networks a lot, where the load on the network, and you can think about load as being throughput, the number of messages that are being sent at the same time. Well, as the load goes up, many networks will have different properties on how gracefully the latency increases. So for example, to give you one example of this, if we think about this example here, you'll notice that the latency of this network is 1, 2, 3, 4 hops to send a message, given the way I've drawn it, if there is no load at all. But under higher load, all of a sudden, the latency of a message may go up because it may wait for another message in the system. So that's one simple example of how the more load there is in the system, that load may manifest as higher latency in these messages. Okay. So yeah, so like one way to sort of draw this chart is there's always some minimum latency, like 4 hops in the last diagram, that you'll be at under low load. Maybe I should have drawn that line here. You might make some routing decisions or some other decisions, and I'll come back to this later in the talk, that kind of increases the overall minimum latency in the system. And then when there's no load at all, that would be like the system right here. We were assuming that routing was free in the last slide. And then as we begin to increase load, you start to get worse and worse, right? Like, is that at some point you sort of have, this is the maximum number of messages that I can send per second. And that as I get closer and closer to that peak rate of the network, it will begin to, the latency of these operations will really begin to slow down. So a general rule of thumb you'll see in any system is that as you build a system that gets under higher and higher load, the latency will go up. And in fact, your assignment for implementation will certainly have this property as well. Okay, so let's talk about a few topologies. So what is the one topology that we've talked about so far in this class? Not in this class, so far in this course. I've put a mesh on the screen. But what was the one network topology that we've talked about so much so far?
Bus.
A bus. So what's good about a bus?
Simple.
It's simple. That's often the best answer to any question of what's good about something. It's simple. What else is good about a bus?
You get broadcast for free.
Yeah, I mean, it's sort of everything is broadcast to everybody. They took your answer, sorry. And yeah, so it's easy to implement, it's simple, it can be cost effective for very low numbers of processors because everybody kind of gets to talk to everybody for free. What's bad about a bus? There's one single shared resource, so there's potentially tons of contention as we scale load. Any other? It's sort of, it's hard to scale bandwidth on a bus because like sort of the same number of wires reach everybody because you have to scale broadcast as well. There can also actually be some because you have all the clients that all need to be connected with the same wires, there's actually some energy and electrical load issues as well that makes it hard to scale a bus. So if everybody connected to the same thing is the simplest topology, what might be the next simplest topology? Okay, so ring is a perfectly excellent topology. I have that. It's pretty simple. I would say that even simpler is what I have here, which is every node is connected to every other node, which is commonly called a crossbar. So a crossbar, every node has a wire connecting it to every other node. And it may be easier to think about a crossbar like this, so I don't duplicate the nodes in the system, just to make it more clear everybody's connected to everybody else. So the cost of a crossbar, what's good about a crossbar is that we don't have to worry about interference or these blocking issues at all. Everybody's connected to everybody else, which means regardless of what pairs of nodes need to communicate at any one time, everybody can always send to everybody else. The problem with the crossbar is that if I have n nodes, I'm going to have n squared wires and n squared junctions. And so crossbars are very expensive to build because of their cost. There's a large number of resources to connect everybody up to everybody else. And unless everybody needs to communicate at the same time, perhaps we can do better. And just to show you sort of some of these crossbars, here's two modern systems built by by Sun, and then Oracle after they got acquired by Sun about 7 years ago now. This is an 8-core processor. Well, you can count the cores: 1, 2, 3, 4, 5, 6, 7, 8. And the interconnect, CCX, is the crossbar that connects every core to every other core. And it's pretty interesting that the die area of the crossbar is approaching that of a full core. So that's that n² effect coming into play here. And in fact, a later version of this processor had 16 cores with 8 L3s. So every 2 cores shared one of the parts of the L3 cache. And then there's a crossbar between all of those cache controllers there. So it's a pretty heavy, pretty gnarly little interconnect there, but it's simple in that everybody can communicate with everybody else. And if you could imagine like taking the n² effect out to 32 cores or something like that, that's probably going to be you'll have half your chip being a crossbar at that point. It may not be the most effective use of silicon. Okay, so you suggested a ring, and a ring is another useful way to organize these nodes in a network. And so in a ring is exactly what you expect, is every processor is connected to 2 other processors. So I agree that a ring is pretty simple to create. It has O of n cost, because with n nodes, there's n links. What's bad is that its bisection bandwidth is what? If I cut the ring in half, I essentially have O of 1 wires crossing it. So this bisection bandwidth is very low. And it potentially has high latency, because if I want to send from 0 to 1, that's very low latency. But if I want to send from 0 to 2, that's higher latency. If I want to send from 0 to 3, is that high latency? You're assuming it's bidirectional. And so some rings are unidirectional and other rings are bidirectional. So if this was a unidirectional ring, it could potentially be very high latency. Or you could architect a more complex ring that could send messages in both directions. And then you would have overall half the average latency.
What would be the advantage of a unidirectional ring over a bus?
Over a bus?
Yeah.
Well, a bus is contention. That's a simple example. So in a ring, 0 to 1 and 2 to 3 can send simultaneously. Or 0 to 1, 1 to 2, 2 to 3, 3 to 0. They can all send messages simultaneously. On a bus, it's a shared common substrate that every node is listening to. So you would not have the simultaneous behavior. That would be a simple example. Yes?
Is there a difference between having a bidirectional ring or 2 unidirectional rings?
This is a great question. I'll come back to that in 1 second. Another example, Isha, is a bus you're going to have to arbitrate. Whereas a ring, if you only have a single link between 2 parties, you may have much simpler arbitration to figure out who gets to talk and when, because only one person can be sending in that direction at a time. So does anybody know what is the interconnect in a modern Intel processor in your laptop or your a ring? Do you know? And that's right. And in fact, it's a couple of different rings. In fact, it's 4 different rings, I believe. And so this is how the clients, the nodes in a modern Intel chip, are connected to that ring. So we have 4 cores in this diagram. Every core is connected to the ring. The memory system is connected to the ring. That's what's labeled as the system agent up there. And also the graphics chip is connected to the ring, the integrated graphics chip. There's 6 interconnect nodes, 1, 2, 3, 4, plus graphics, plus the memory, or plus the system agent. And an interesting thing is that and it's a unidirectional ring, but every node is connected to the ring twice, which means that you can choose if you want to send from this node to this node, you actually have a choice, right? You can send this direction from here, or you can send this direction from here, which means that you can have a unidirectional ring with unidirectional complexity and signaling and still get the benefit of being able to take the short path. And so there are two connections. So the complexity a lot lies in, for every node, choosing which connection point you want to use, not complexity in arbitrary two directions down a link. And so for those that actually care, there are various different rings. Some of them are for sending requests. Others are for reporting your Snoop results, which we talked about in that lecture. Others are for acknowledging Snoop results. And the last one is the data ring, the fat one that I illustrated here, which is where it's a 32-bit wide links to actually send the data back for some of these requests.
Data ring is always the size of cache lines?
Well, that's not the size of a cache line.
It's not, okay.
Yeah, a cache line is 64 bytes.
Okay, is there, I guess like it's economic, it's like financial economy in terms of like having fatter data line?
Correct.
But that would mean like you have to send like twice. So it's like twice the latency?
Yeah, I mean, basically, if you want to send a cache line over over a link in the bus, that will take 2 clocks to get it there.
Why did they choose to do this?
Well, I mean, there's always going to be a hardware resources trade-off against performance. That's essentially the trade-off that they made. And so, first of all, this is happening whenever the processor is taking an L2 cache miss. And not just an L2 cache miss, but an L3 miss into a non-local slice of the L3. So notice how the L3 is actually partitioned across the cores. So even though it's an 8 megabyte L3, there's 4 2 megabyte partitions. So an L3 cache hit in your local partition will get serviced more efficiently with lower latency than an L3 cache hit in another core's partition. So an L3 cache, an L2 miss may create a network request that goes through another partition of the L3. It will get serviced on the data bus by 2 over the data bus, so for 2 cycles. So you already just took an L2 miss, so you probably just took 10 to 15 cycles worth of detecting the L2 miss. The fact that you're getting the data from the remote core in 2 cycles over the link rather than 1, maybe not as big of a deal as it seems if you're just thinking about it in isolation. Yeah, exactly. I mean, there's probably a good, I think I had a slide in the cache coherence lecture. I think we said that the L3 hit time was something on the order of 20-some cycles or something like that. It's different depending on whether it's local L3 or remote L3. And 2 of those cycles in those 25 are getting that cache line over the ring bus to the appropriate place. That's a good question. Okay, so let's talk a little bit about a mesh. A mesh is a direct network because the nodes are sitting there in the network. O of n cost because on average there's 1 link per node. The average latency is square root n. Why do I say that? N is the total number of nodes in the mesh. So if there are n total nodes in the mesh, the average latency is proportional to roughly one of the edges of the grid. What's the diameter? The diameter would be the diagonal. Good. So here's a question. If I pick 2 nodes at random, or what's one potential problem with a mesh network? This is also a problem in our ring as well, is that you don't know when you want to send from A to B how long that's going to take, because it very much depends on A and B. So if A and B happen to be right next to each other, super low latency message. If A and B happen to be the 2 corners of the mesh, it could be a very long message. So if you happen to pick a processor. So one of the nice things about the ring is that regardless of what processor you are, on average, you have the same latency to every node. In the mesh, imagine I said that you got to pick which node in the mesh you wanted to be. Which, if you were thinking about optimizing your communication costs, which node would you pick? Yeah.
Probably one towards the center.
Yeah, you'd probably want to be the center because on average you'd be closer to everybody else, right? So people could send you messages with lower latency. So now we have certain processors that are just intrinsically disadvantaged in the system. So imagine that like you break up your system into you break up your code into tiles because it's like the grid solver. You expect everything to run the same amount because they're all doing the same amount of work, and then you're just like, oh gosh. There's a problem because the communication on some of these things is higher. I guess the grid solver example would be a bad one because all the communication would be local. But so this mesh is actually very close to what you see in this new Xenon Phi. The new Xenon Phi has 72 cores. Each of those cores are paired up into tiles of 2 cores. So 2 cores share a cache. So there's 36 caches that are on this network. And you can think about that network as a 6x6 mesh. And so if you want to send from one of the processors on this mesh to the other, the routing is going to be move in Y and then move in X. So the routing policy is send here and at some point turn and move in this direction. So it's the primary feature of the Phi network is a 6x6 mesh that's routed sort of in a Manhattan distance kind of way. So if I asked you to correct this problem of there's like an asymmetry in the average communication cost from a node, how might you, can you think of a way you can improve the mesh? So we can take that idea of a ring, right, and we can turn the mesh into a mesh of rings. And so I can connect this node all the way to the node at the top. I can connect this node to its counterpart over here. And then I get what's called a torus network, right? That looks like this. And so the torus network is like a mesh, except it has twice the bisection bandwidth. It has twice the bisection bandwidth, and it also has a more uniform, or a much more uniform average latency across the nodes. But it can be difficult to lay a torus out on chip because the chip is flat, and so things need to move on top of each other. You have to go through some different metal layers and things like that. But you do have a much more powerful network. We can always start to lay our networks out as trees. Like for example, this is a nice planar tree, which you can imagine laying out on chip. What is the problem with trees? So actually, let me step back this way. This network here, is this a good network for the grid solver? Or is a ring a good network for the grid solver? Because there's a nice little correspondence between processors here and what processors they can communicate with the lowest latency. Is that in a problem like the grid solver, every processor needs to communicate just with their neighbors, right? And so a network like a mesh or a torus really captures that locality really well. All of these messages can be sent in parallel compared to a ring or a bus where there would be blocking and conflicts. A tree network would capture the locality of any divide and conquer program really well. But there could be a problem if I wrote an application that needed to send a lot of information from 5 to 9. Because the bandwidth, if only 4 and 5 communicate and 6 and 7 communicate, that's great. But if these nodes over here need to do a lot of communication with these nodes over here, all of that communication is going through one channel, right? So I have a much lower bisection bandwidth if I made a cut through the network like this or like this. And how might you fix a problem like this if I had a tree And I was like, gosh, I'm really constrained by this link here. One answer would be, let's go move to another network, like a mesh or something like that. But what if I told you it needed to be a tree? There's a big hint on the slide, right? Is you could take some of those critical links and you could make them much faster. Now, if you do that, you're kind of defeating the purpose of a tree, because you're saying, look, I believe that these are the links that should be used the most because applications have spatial locality. Yeah. You could have multiple routes, actually. You could build a second network down in this direction, which would be another way to do it. Multiple routes would be like equivalent to this fat tree, actually. So this is often called a fat tree because it's thick at the top. If I built another network down here with skinny lines, it's like the same thing as me folding it back over. So.
Exactly, but maybe laid out differently.
That's true. You could lay it out differently, and we'd have to think about whether or not, like under what situations that was a good idea. But yeah, exactly. I agree. So you'll need to have a situation where the contested links were the fattest links. And of course, you can take crazy topologies out to wazoo. You could go with, like, for example, a hypercube. And a hypercube means we're going to start drawing links in all the various dimensions. And a hypercube is a network that is, in general, will have a radix of log n, which means every node in the network will be connected to log n other nodes in the system. And the bisection bandwidth of a hypercube network is n over 2 in the traditional hypercube network. So you'll see like 60 hypercubes in some of the old supercomputing systems. Probably one of the most famous hypercube networks was the SGI Origin, which was a computer that we wrote code on in 418 up until about last year. So these systems provided very, very high bandwidth over large numbers of nodes, and you paid a lot of money to do so. You paid a lot of money to do so. These days, common networks would be multi-stage networks, where, and I'm showing you one example of that here, which is an omega network. These networks are called multi-stage logarithmic networks, and they usually have a cost. There's like a hybrid sort of between a full crossbar and something like a ring, where you have O of n log n cost, because you have n over 2 switches, and you're going to make log n switching steps. So the latency is always going to be log n. And can anybody come up with an algorithm, given this network, for routing a message to a particular processor? And I've given you a big hint here by showing the bit code of the output processors and the input processors. Yeah?
The first part, it seems that you have the last 2 bits of the left side code
Okay.
to decide which of the 4 you go into the read.
So it definitely has to do with the bit code of the network. You're getting there. Yeah?
So once you get to that first link, you make decisions to go.
So there's no real decision here. So you can start thinking about the problem from right here. So here, let's say we wanted to send to 1.
So 1 is 0, 0, 1, so go up, and then down.
Yeah, top, 0, 0, top, down. And if we wanted to go to, let's say, 7, it would be 1, second link, 1, second link, 1, second link. So you can actually come up with your routing policy directly off the bit code for the destination, which makes routing pretty simple. So that's sort of cool. Okay, so in any of these network topologies, you can kind of you can compare and contrast them a little bit by asking, okay, are they direct or indirect? Are they blocking or non-blocking? What is the cost in terms of the number of links? And the cost in terms of the number of links, you can think of as, well, what would the chip area be if I had to lay one down? And then what is the latency of getting messages on average, or in the worst case or the best case, between any nodes? And of course, this is a very simplified view of everything. Yeah.
I have a question for the like mesh and tree. In order to
Okay.
utilize the like traffic locality, the assignment of stuff to the cores needs to, I don't know, correspond correctly, and I was wondering
Absolutely.
where or how that.
So this is NUMA in some sense, in its essence, if you think about the communication network as being part of the memory system, right? So we could think about it as, well, it kind of also depends on where memory is. So let's look at this topology. You could say that every node in the network might have its own DRAM controller. That might be true. Or you could go back to, like this ring example, and, well, memory is just a node on the network. So memory in some ways is equally distant. So this core is the closest one to get to memory, period. Now, of course, the 1 or 2 cycles that the ring bus, multiple hops on the ring induces is nothing compared to the 100 and so cycles that you're gonna take to go out to memory. But even this one, there's actually a core that's preferred to memory in this case, actually. And in fact, I don't know if that's on purpose or not, but notice that the graphics processor has the highest memory latency tolerance of any component in the system. It does make sense that it's the farthest away because it can hide that latency. I don't know if that's actually in the design or not, but yes, if you're working on a machine and you want to really optimize communication performance, the locality and layout of your program will have to absolutely be reflecting of the network topology. Imagine if you have a mesh network and you're doing some big scientific computing code like the grid solver. Imagine you partition it perfectly properly and then like randomly shuffle the assignment of worker threads to processors. You're in bad shape pretty quickly. Exactly. Okay, so let's talk a little bit about, given a topology, let's get messages from one area of the network to the other. So there's kind of 2 major ways to think about, if I'm going to send a message to, let's say we're all nodes in the network and I want to send a message to one of you, and let's say that we all have links to our neighbors, I can do one of 2 things. I can treat this like a phone call, or I can pick up the phone, I can dial a number, and that, which is not true in a modern context, but was true with original phone calls, I can reserve space all the way out to the sender, or to the receiver. And as soon as that channel is reserved, I can start sending my information. So we'll call this way of thinking about things a circuit switch network, because back in the old days, there really was a circuit that we created, an electrical circuit between me and the receiver, and my audio would move over that circuit to them. Alternatively, we can think about it like everybody in the world probably thinks about networks these days, because we are young and we've only dealt with packet switch networks, is we can think about dividing our big messages up into a bunch of packets, and then each of those packets being sent through the network however the network wishes to route them, which is how everybody is familiar with the internet working. Okay? So, yeah, okay. So let's talk a little bit about the granularity of communication. So if I want to send you a message, that's 1 unit of data. It's whatever I want to send. It's a web page. It's a video file. It's a news story. And that message might need to get broken up by a communications protocol, IP, TCP, whatever, into a bunch of fixed size packets, or variable size packets for that matter, because that is the unit that the protocol is going to operate at. And in a hardware and on-chip networking, they're actually, the packets themselves might get broken up into smaller units of control, which are often called flits or flow control digits. And those are the individual units, the granularity at which pieces of a packet or information is going to flow through the network. So you could say, well, why doesn't the network just make smaller packets? Really, the answer to that is we have communications protocols, we have networks, and we have applications. Applications send messages. Protocols break those messages into packets. Low-level networks might have a different mechanism to handle flow control, and that is the flit. Okay, so just some terminology in networking. So every packet I might send over a system is going to have a little bit of information in it, right? I'll have a header. The header might say, here's where the packet's going. It's going to node A. And then it will have some contents. And it will have a tail. And the tail usually has things in it like error correction or a checksum so that the header tells me where the packet's going to go. So when I receive the header bits, I know immediately where I'm going to send it next. And once I've received all the bits, I receive in the tail usually a checksum, because what I'm doing is I'm going to immediately make sure that the packet or the data that I got was valid. And I can terminate or react accordingly if the checksum doesn't match the contents of the message. So this is your basic packet. If you've taken networking, this would be very, very familiar to you. Okay, so here's a question. Let's say that 2 packets hit a switch. One came in from this link on the right. Another came in from this link on the left. And both of the packets, just because where they need to be routed, where their destination, need to go out this link to the left. So this is a switch, right? It connects incoming links to outgoing links. And I now have 2 different communications, one the red communication, one the blue communication. And they both need to use the output link. So what are my options? Imagine that you're now designing a yellow box. How might you what are some options to handle the system? I can think of like 2 or 3 different ways that I might deal with this. Yeah. Okay, so one answer would be say, sorry buddy, there's contention here and you can drop one. Perfectly valid answer. And presumably, the higher level communication protocol will detect the drop and then try and resend, in this case, let's say the blue packet, at some later time. Perfectly reasonable solution. What are other solutions? Yeah?
Send one in its entirety and then the other one.
And so, to be more specific, it's if I'm going to send the red packet immediately, I just received the blue packet, so I need to augment my system with a buffer that has to buffer the contents of the blue packet, and then it will send it at some later time. So if answer 1 was drop, answer 2 was buffer. Good, buffer and delay. And is there a third answer? And I kind of have kept the third answer out of it by the way I've defined the problem, but yeah?
The network topology lets it like reroute it another way.
Good, exactly. I told you they both needed to go to some node this way, but networks, routers do this all the time. Is they say, well, you need to get over here. This link's, under duress or highly contended. Well, I'm going to send you this direction and hope that the router over here might have a better answer for you. So you can also reroute, which is often called deflecting a packet, because you can call it bouncing off the router. So those are 3 perfectly reasonable options. And in fact, you could take a whole course or a whole series of lectures on how to make these types of decisions. Now, in this lecture, or for the remaining 15 minutes, I only want to consider the buffering option. And here's one more question, is why doesn't this situation happen in a circuit switch network? Remember when I said that let's think about this like a telephone. Why can this not happen in a circuit switch scenario? Yes,
Because
Dave.
that path is totally reserved for one of the 2 links.
Exactly. So if we're in a packet switch scenario, we send a packet. We want a router is going to take a look at a packet. It's going to figure out which next hop it should go along. It may reserve that one link, and it will send the packet on its way. In a circuit switch scenario, the whole point is to reserve the entire channel all the way to the destination. So all of this waiting or buffering or delaying occurs at the time where you pick up the phone. Or when you dial the number, I guess. Sorry. When you dial the number. And then the circuit gets created, your bandwidth is reserved, your channel is reserved, and nothing can ever happen. So that's exactly what's going on here. And so what's good about circuit switching is that all the costs you pay are up front. There are costs that happen every time you make a phone call, and not every time a packet is sent to communicate data from the phone call. So it's good in that there's very little overhead, and pre-allocating resources is useful because you don't have to worry about any of these complex problems that we just talked about. It's bad because it's a potentially terrible use of the network. you have to reserve all of this space. You might send a message, and the message might have already gotten over to here, but you're still holding on to the network until the entire communication has been completed. So it's a very, very coarse-grained oversubscription of the network. Okay. And as we know from our more dynamic internet networks, and you can imagine very dynamic on-chip networks, that a more fine-grained packet-based switching system is far more efficient most of the time. So let's talk about the simplest possible way of dealing with moving packets through the network. And the simplest possible way is often called store and forward routing, which is going to work at the granularity of packets. So imagine we have a message, a message that has, in this case, this is one packet. What I'm drawing here is one packet. So it has 4 pieces to it. And the way this is going to work is that if I want to send the packet from the source to the destination, and let's say it's going to travel this route, okay, is this router says, I have this one packet. I need to reserve this link, and then I will send the packet over the next 4 ticks. So I reserve it, 1, 2, 3, 4, and then I release it. And now that link is available for anyone else to use. And we will continue to do this. Reserve the next hop, 1, 2, 3, 4, and so on and so on, right? So what is the amount of time it takes to send one packet from the source to the destination in this scenario? So what is the amount of time it takes to send one packet between 2 adjacent nodes?
The time it takes to send the message and the time it takes to reserve the link.
That's right. So let's just say that the reserving the link is free. And in this scenario, the time it takes to send one packet, and I won't say a message, I really mean a packet here, from one node to the next in the network, or one router to the next in the network, was 4 clocks, 4 ticks. And the total amount of time, the total latency of sending the message from the source to the destination was what? It was 3 times that, and it was 3 times that because the distance was 3 hops on the network times the amount of time it took me to take 1 hop was 12 total clocks, right? So the latency was the packet transmission time per link times the network distance of the communication that I need to do. And of course, compared to circuit switching, this was nice, right? Because we were only using one link at a time. So once we got to this point, like if we were in the middle of transmitting the packet from between these 2 nodes, some other packet could have been communicated over here or even over here, right? Yes, Isha.
The only advantage of the link is free is when the buffer is also free, right?
Oh, well, in this particular case, I made it simple by making a buffer to be the size of one packet.
Right.
But we could certainly, if I had more room on the slide, I could add more buffering so that another send could be coming in here simultaneously with reading this out. Yes, but I think I only drew one packet, one buffer, or a 1 packet size buffer on the slide just because okay. So, this is a pretty simplistic way about going about things, right? Like, what would be the solution to reduce the latency of sending this packet? And what term from class should be in everybody's head right now? Sorry? I heard it. I don't know from whom. Pipelining, yeah. So we can pipeline the communication, right? So right now, communication is very much not pipelined. So let's get to the next thing. Okay. So let's pipeline the message send. So let's send the first part of the packet that contains the header. And remember, the header is going to contain the destination. So as soon as the new router receives the first chunk, the header, it can start taking that information, and it can begin to reserve the next link in the process and send it over, right? So after 2 steps in the process, the first part of the packet has gone 2 steps. The second part of the packet has gone 1 step. This is the second part of the packet. And the last half of the packet still hasn't been sent yet, right? So if I continue on, then I look like this, and so on, and so on, and so on, right? So my latency now has dropped from 12 units, 4 times 3, to 6 units, the amount of time for the head of the packet to arrive, 1, 2, 3, 4. Sorry, 1, 2, 3. Plus the amount of time it takes the rest of the packet to arrive. Yes?
Would this be highly annoying if like something just drop, like each one start dropping one segment of the packet?
Well, you can think about this as the minimum granularity of flow control will be the packet. Before we, I would think about it that way. Is that once that link is reserved, it's reserved for the packet. That would be a good simplifying assumption to make in thinking about this. We're going to not think about flow control at a lower granularity until the next slide. But there is one interesting thing, is maybe I'll ask a slightly different question. Oops, sorry. So here, the amount of buffering that I need is 1 packet. This is the original formulation. So here we're still sending packets. We reserve the link, and then over the next 4 cycles, we send the packet. We just start sending the packet over the next link, pipelined with receiving the packet over the previous link. But we're still sending packets. So what happens if, something I didn't have on this illustration, is if we cannot immediately start sending the packet on the next link? Because imagine it's busy for some other reason. So I don't have a diagram of this, but what is this diagram going to look like in the pipeline case, which is called cut-through flow control, because like the packet is being cut and sending, is sent over the next link while the rest of it's coming in. What happens if we cannot start sending the link, the packet over the next link, say because the link is busy for whatever reason?
So assuming you couldn't start rerouting it?
Yeah, let's not think about, because I said we're not going to deflect in this lecture, so we're only going to buffer and send, right?
So you would keep filling up the current buffer, and then when it opens, you continue pipelining again?
Yeah, exactly. So what you do is, remember, this whole system is working in terms of I only send packets. So when I get a link over the next 4 cycles, I send the packet. That's the unit of transfer in this network, is a packet. So in this case, what would happen is that over the next 4 cycles, the rest of the packet would come in, and it would get buffered. And then when the link opened up, we would start moving forward again. So it's interesting that even though this cut-through example has significantly reduced the latency by pipelining, it actually has, oops, let me get to the end here. It actually has the same worst case amount of buffering in all of the switches. It means that since the network sends packets, it must be able to buffer a packet if need be. Yes? And yeah, absolutely, because you say, look, I need this link. So what's the deadlock that you're referring to?
I mean, no one will be able to like send messages without, if you don't allow the dropping policy, and if A wants to send it to B, B wants to send it to C, C to D.
And on some topology, that may not be possible if all the queues are filled and stuff like that. Absolutely, and deadlock-free routing is a major topic of if you were taking a course, an advanced course on network routing or on system-on-a-chip routing. And so this lecture does not contain any algorithms for avoiding deadlock. One way is always start dropping things, and then you have the live lock problem as well. So making sure that you make forward progress is something that's very challenging in these networks because they can grind to a halt effectively because of dropping and things like that. Okay, so does anybody see how the buffering requirements of both of these systems are the same? if the head can't make progress, the tail just catches up, and I've got to keep the whole packet because I'm not dropping anything in this lecture. Okay. So the idea that the solution to this in most modern systems is to drop the level of granularity in managing buffering and flow control from the packet down to something smaller that the network controls, which is typically called the flit, which was on that previous slide. So I can take a packet and divide it into a small number of fixed size chunks, and the network is going to reason about flow control on these tiny little flits, which might be significantly smaller than whatever your communications protocol says a packet is going to be. And so if I want to send a packet, which is broken into 4 little pieces, head, body 0, body 1, tail, I'm going to route on a per packet basis. So the same thing's going to happen is I'm going to reserve space in the link. I'm going to go, and over the next couple of cycles, only the following flits are going to be sent on this link. But now, and I don't have an illustration for this, imagine if this isn't just the destination. Imagine this is in the middle of the network. If the head stops, then all of the subsequent flits stop where they are in the network. So instead of them keep coming and getting buffered, they all stay where they are. So now this packet can be distributed throughout the network, and every flit just follows the flit in front of it in line. So now the amount of buffering I need is determined by the network and not the communications protocol. It's the size of a flit. And that my packet is now distributed throughout the whole network. Does the difference between this slide and the last slide, was that okay? One of them sent packets and just happened to pipeline the sending of the packets. Now we're sending individual flits. And we're storing flits in the network. And every single packet will be potentially distributed across a packet size number of network nodes. So you asked me a little bit about deadlock, and this is often called wormhole flow control, because the packet moves through the network like a worm, right? Like when the head takes a step, then all the subsequent flits all go, oh, okay. And so on, and so on, and so on. The problem is what happens in a situation like this. So imagine now that I'm drawing a buffer in every single switch that has room for 2 flits. 2 flits. And I have 2 different packets here, a gray one and a blue one. And the gray one is moving in this direction. And the gray packet's head flit is blocked because the red link here is occupied. The blue packet is traveling in this direction and needs to leave the router in this way. But the blue packet can't make progress because it's behind the gray packet in this queue. And the gray packet's not getting out of that queue because it's waiting for its head flit to keep making progress. So even though we could have used the blue this link for the blue packet and sent it on its way, we can't because the blue head flit is behind a gray flit in the network. So solving the problem should just be jumping out at everybody because like in software, this would not be hard to solve. How would you solve this? Well, increasing the buffer size will not help. Let's say this buffer is infinitely long. The problem here is that the buffer is processed in order. And the head of the queue cannot make progress because the head of the queue is the gray flit. Behind it in the queue is the blue flit. So a bigger buffer would not help here because I've in some ways said, look, I process my queues in order.
Can't we choose to, if the head of the packet is blocked, receive the rest of the packets?
We can do that, but it's still, that's not quite solving the problem. We can receive, if we had more buffering, we can receive more blue flits if we wanted to. But I still am not going to make progress on the blue flit if I'm processing everything in the queue in a FIFO order.
When like one packet is stalled, like when read is stalled, you want to go on to the next packet which needs to be done.
You'd like to be able to process other things in the queues, right?
Yeah, you want to open the order.
Right. So instead of moving to an out of order model, the way it's commonly modeled in networks is to be virtually different queues. So when you read about these systems on a chip, they're going to talk about virtual channels. And when you're sending a packet, you're going to reserve this virtual channel to send flits on. Those might be implemented as the same buffering logic in the switch with out-of-order execution trying to find the first head of all the different channels. But logically, they are different channels. And so this is how the modern networks, they have virtual channels that are implemented on top of the low-level physical network channels and buffers. And the virtual channel mechanism is the mechanism that's very, very valuable to do things like deadlock prevention. Like, for example, most of the channels might not allow dropping packets because dropping packets is messy. But you might have one of the virtual channels always be able to drop packets, which might allow you to always make progress somewhere and things like that. So once you've decoupled your physical buffers from the logical notion of a communication channel in a network, you now can start implementing software techniques for deadlock avoidance, quality of service, and all of the things that are going to be really, really important to efficiently using the physical links that you have. So anyways, at this point in the lecture, I stop because we're very much at modern research in computer science and computer architecture of how to design very efficient interconnection networks and routing protocols on these networks, especially in the face of sort of modern different types of interconnect topologies and things like that. So the takeaway from today's lecture, which is kind of like a one-off lecture, which we won't come back or build too much on this in this class, is a modern multi-core processor is a network, and policies for routing messages between the cores are very, very critical to the overall performance of these systems. And if you work at Intel, you work at NVIDIA, and you're on the team that's responsible for the network, you're in a very, very, very valuable part of the company these days. So I'll leave it at that.